Welcome to Math 1324, Lecture 4.3 on the logarithmic function. Today's brief pause before we begin is a question for you to think about. What are the things that you like to do but haven't been doing? I'm recording this video lecture in the fall of 2020 when we're in the middle of the COVID-19 pandemic. And so many of us have stopped doing a lot of things that we like doing. But there are still things that we can do with a reasonable amount of safety. But this is a good question at any time to think about what's really important to you, what's enjoyable to you, and how do you keep yourself energized. I think especially as we move along into our career and family take up so much time and energy that we forget to feed ourselves, to feed our spirit by doing the things that we enjoy doing, the things that bring us energy instead of necessarily take energy from us. This is also a good question as you're pondering career choices, to think about the things that you like to do and how does that map into the kind of job you want to work at. Maybe not even just the type of work that you want to do, but the environment you want to work in. Do you want to move around more? Do you want to be in an office? Does that seem good? What are your hours, etc.? And these can be things that can help you make a better choice that fits your personality, your passions, and your abilities. Here's a quote by Goethe. Things that matter most must never be at the mercy of things that matter least. Stephen Covey, the 7 Habits of Highly Successful People, also uses this one. That I think for most of us, we get caught up in the dailies, the to-do list, and those kind of things. And we often forget this thought, that what's really important to me and how am I making space for that or time for that in my life. And one from The Lord of the Rings, J.R.R. Tolkien, all we have to decide is what to do with the time that is given us. Casey Mulgrave, is that her name? Has a great song called Follow Your Arrow, and there's a line in there that says, do what you want to do because you only have so many trips around the sun. So I encourage you to take a little time and think about the things that you really enjoy doing, the things that feed your spirit, that give you energy. And even if you're listening to this in the middle of the COVID, how can you take care of yourself with those kind of restrictions? I know for me that just getting up early and taking a walk and a run in the morning makes a huge difference in the days that I don't do that. Okay, so today we're looking at logarithms, logarithm functions, and logarithms. This is a new topic for many people, so it could be a little bit challenging. Logarithms are the inverse function of exponentials. So just as subtraction is the inverse of addition, logarithms are the inverse of exponents. So for example, on the left in blue, you see 3 to the power of 4 equals 81, right? That's an exponent. We're very used to that. 3 to the power of 4 means 3 times 3 times 3 times 3, which equals 81, okay? Most of us are so familiar with exponents that sometimes we see this 3 to the 4th power and we say, oh, that equals 12. That our brain is trying to help us out by making a shortcut, but of course that's a product and not an exponent. So be careful with exponents that you don't pay enough attention and you make a simple mistake of multiplying these out. I see this a lot with 3 squared and people writing 6 instead of 9. Okay, so we have 3 to the power of 4 equals 81. Well, we can write a logarithm. And this says log base 3, it's a base 3 exponent, of 81 equals 4. And so there are 3 parts to both a log and an exponential. We have a base, an exponent, and an answer. In the log, we have the log with the base written at the base of the word log of the answer equals the exponent that will give us that. So basically, when you're seeing 3 log base 3 of 81, you're asking how many times 3 multiplying by itself do I have to do that to equal 81? So again, base exponent equals answer, log base b of y equals x, base raised to an exponent equals the answer, and then for a logarithm, the log of the base of the answer equals the exponent. So you can see kind of how, hopefully that shows you how there are inverses. In ancient times, logarithms were calculated very painfully, mainly by monks, and then they would make these huge long books, thick books, heavy books with just lists of logarithms in it. And so before there were calculators, there were these tables of logs. Until the development of calculators and computers, logarithms were the only effective tool for large-scale numerical computations. They are no longer needed for this purpose, but logarithmic functions still play a crucial role in calculus in many applications. So because our calculator can do the calculations, we don't need logs as much as we did in the past, but we do use them for calculating change in calculus. To solve logarithmic problems, what we're going to do is convert to an exponent and then calculate. We're much more familiar with exponentials. So it's very important that you kind of see the relationship between the pieces, the elements of a log and the elements of an exponent and where they are. Remember that you have log of log at a certain base of the answer equals the exponent. And on the exponent side, we have a base raised to an exponent equals the answer. These are the same 3 parts as we saw in the last slide. Again, here's an example. Log base 2 of 16. If we're trying to find the answer there, we set that equal to x. Then we rewrite it as an exponent. Base 2 exponent x equals 16. So 2 to what power equals 16. And if I'm trying to figure this out, I can actually just do this on my fingers and calculate. 2 times 2 is 4. That's 2 of them. Times another 2 is 8. 4 times 2 is 8. And 8 times 2 is 16. Well, that's 4 2's. 2 times 2 times 2 times 2. So the exponent is equal to 4. So try these problems. You might want to hit pause and see if you can calculate each of these by first translating them into an exponential. You'll notice that the x is missing for all of these. So that's the first thing you want to do, is set them equal to x and then convert them with the base, the exponent, and the answer, and then solve. So for 17, we have a base of 4, the exponent is x, and the answer is 64. 4 to what power equals 64, and the answer is 3. For 18, we have a log base 5 of 125. So the base is 5, the exponent is x again, because we would set this equal to x, and the answer is 125, and this answer is also 3. For 19, we have a base 2, exponent x equals 1/4. Now this one's a little more confusing, okay? But remember, whenever you have this, a fraction, and you have a 1 in the numerator, remember that this is just going to turn the exponent negative. So I can say 2 to the x equals 4. What would the x be? Well, that's squared. But because the 4 is in the denominator, remember we use a negative exponent, because that's all a negative exponent means, is that it's in the other side of the fraction. If it's in the numerator and a negative exponent, it moves to the denominator. And if it's in the denominator with a negative exponent, it moves to the numerator. Okay, so when you're seeing these fractional logs with a 1 in the numerator, realize you're dealing with a negative exponent. Same thing with with 20. 3 to the power of x equals 1 over 27. And again, 3 to the power of 3 equals 27. Because it's in the denominator, it's going to be a negative 3. Your calculator will do any base problems by using the math button, but it also has two buttons that are specifically for two types of logs. And the first one is a common logarithm. Common logarithms are when there is no base number written, and these are base 10. Now, why is that called the common log? Can you figure that out? Why is base 10 a common log? Well, base 10 is the base of our numerical system. We have a decimal. DEC, dec, means 10 in Latin. And so we have a base 10 numeric system. And so that's why the base 10 log is called the common log. Okay? So notice if there's no number written for the base, then this is a common log. It is a base 10. If there's no number like a 2, a 4, an A, whatever, then this is a common log. And we know that common logs all have base 10. If you look on your calculator right to the left of the 7 button, you'll see the button log. This is a common log button for your calculator. So you can calculate common logs with that button. Natural logarithms are when the log is written as in ln, log natural, okay? Right beneath the button for log on your calculator is a natural log button, ln, okay? And these are base E, or Euler's constant, you might remember from the prior lectures. And why are these natural? Well, these occur in nature. When bacteria grows, the carbon dating of fossils, the way carbon decays, the way we measure earthquakes, the Richter scale, all of these use a base E for the exponential, and so the logarithms are also base E. And so when you see ln x, this is the same thing as log base E. Do not write log with a little e underneath it. Write it as ln. That's the proper notation. Natural logarithms are quite common. I should probably use it. Are quite frequent. And so you want to write ln, not log base E. Okay. And then, of course, if I am converting this to an exponent, my base is E, Euler's constant. My exponent in this case is y, and then my answer, which is next to the log, is x. So try these again. We just did a handful with different bases. Try these common logs and natural logs. Convert them to an exponential and then solve it. Remember that, again, none of these have equals x on it, so you need to add that in, and then you can convert it. So you can pause here and do these real quick. So for 13, we have log base 10 raised to the power of x equals 1,000. Base 10s are easy to calculate if they're even, because it's simply the number of zeros. 10 times 10 is 100, or 2 zeros, so 10 squared is 2 zeros, 10 cubed is 3, 10 4 is 4, etc. Notice that in 14 we have a base 10 to the power of x equals 0.0001. Well, notice this is 1 over, remember the first place is tenths, 100ths, thousands, 10,000ths. So a decimal is indicating a fraction, 1 over 10,000. That's 1 over 1 with 4 zeros. So again, we know that the exponent would be 4, and because it's in the denominator, it's going to be negative. It's a fraction. 21, we have base E to the power of x equals the square root of e. Well, remember the square root is also the exponent of 1/2. The root is the denominator. The power on whatever's inside is the numerator. Since there's no exponent, the numerator is 1 and the denominator is 2. And since these are the same, we know that the x has to equal 1/2 because we have e to the x equals e to the 1/2. Since the bases are the same, the only way this is true is if x equals 1/2. For 22, we have e to the x equals 1 over e, or e to the negative 1. Again, we can see e to the 1 would give us e, and since it's in the denominator, it is negative. In 23, we have e to the x. Again, if we make it equal to x, equals e to the 8.77. Again, because we have the same base, the exponents have to be equal, and x equals 8.77. And that's what we have in the last example too. We have 10 to the power of x, right? Log base 10 equals x equals 10 to the 74.3. Well, when we ever have this set up, the exponents have to be equal if the bases are equal in order for that to be true. Okay, and this is a fundamental property of logs. We're going to look at it in a minute. So go ahead and try to use your calculator. Pause again for a minute. Use the log button and calculate the log of 53. And then use your natural log button, ln, to calculate the natural log of 0.0068. I just want to give you a couple examples so you get a chance to practice this. You should have got 1.724. The instructions also tell you to round to the 3 decimal places. And then for 27, you should get negative 4.991. And again, you should know that because you can see this is a fraction, a value less than 1. So why does the log a of 1 always equal 0 no matter what the base is for any valid base of a? And I should have mentioned before and I didn't, but bases are always positive and not equal to 0. When you're talking about the logarithmic base, you're talking about a positive value, positive number that's not 0. I guess positive would indicate that as well. So if I rewrite this as a to the power of x equals 1, why does that exponent have to be 0? Because anything raised to the 0 exponent equals 1. So it doesn't matter if I'm taking the log of 1, if I'm taking the natural log of 1, if I'm taking the log base 3 of 1, this will always be equal to 0 because we're going to get a to the power of x, whatever that base is, the base to the power of x equals 1. Well, the x will always equal 0. So these are some properties of logarithms. Let x and a be any positive real numbers with a not equal to 1. And r any real number. So we already talked about the first property, log base a, the log of 1 is always equal to 0, no matter what the base. Okay? In b, we're saying if we take the log base a of a, so if we ever take the log of the base, if this was a common log and we had common log 10, this would equal 1. If we had natural log e, the natural log of e, this would also equal 1. Well, that kind of makes sense if we convert it into an exponential the way we're doing it, because we'd have a to the x equals a. Well, what would be the exponent on that? It would have to be 1. Okay? So when we take the log of the base, the answer is 1. If we take this a step further, if we take the log of the base raised to some exponent, well, the answer is the exponent. It's going to be that same exponent because we're going to say a to the x equals a to the r. What does x equal? It's got to be the same thing. So the log of the base raised to a power is that power. Okay? And D is the inverse rule. It says if we have a base a and we raise it to the power of the logarithm, and remember this is an exponent is the inverse of a log. So what this does is it cancels out. We have the log in the exponent of the same base. Well, then we just get the answer. And this is kind of the rule of inverse functions, right? Because if I add 4 and then subtract 4, I get back to where I started. And so if I raise, if I have an exponential and I put the log in the exponent, then I just get the answer that's in the log. These are very important rules that you're going to need to use. So you need to understand these 3 properties of how to manipulate logarithms. And you need to be able to go backwards and forwards. What I mean is the first one says the product property. The log of a product. All of these are the log of a product, the log of a quotient, the log of a power. So all of these titles are referring to the argument of the log, not the product of 2 logs. Notice that. It's the log of a product, not log x times log y. There is no property for the product of logs. These properties are the arguments, the log of a product, not the product of logs, okay? So that's one thing you have to think about, all right? So the log of a product equals the sum of the logs of the factors. So if I have the log of x times y, this equals the log of x plus the log of y. That's the product property. Now what your brain wants to do, if it sees the log of xy, it wants to make this the log of x times the log of y. It wants it to be really neat. Hey, I'm doing a product on the left, I'm going to do a product on the right. Do not do that. You will have it wrong. So be careful of your intuition here. The log of a quotient. This is again one where your intuition will get you in mistakes. Students love to say the log of x divided by y equals the log of x over the log of y. That is not correct. The quotient, the log of a quotient equals the log of the numerator minus the log of the denominator. The log of the numerator minus the log of the denominator. And the last rule is the power property, and this one's kind of interesting too. So if we have the log of an argument all raised to a power. So again, this is about a power on the argument. If the entire argument has an exponent or power on it, I can bring that exponent or power down into the front. So the log of x to the power of r equals r times the log of x. So we have the product property where we add the logs of the factors for the log of a product. The quotient property, the log of a quotient equals the log of the numerator minus the log of the denominator. And we have the power property that when we have the argument of a log raised to a power, that power can come down in front and become a multiplier of the log. So this is a little bit challenging. I'm going to do the first one, and then I want you to try to do the other ones by hitting pause. Write each expression as a single logarithm using the properties of logarithms. The log base a of 5x plus the log base a of 3x to the fourth. So what I'm going to do, until I'm familiar with these rules, and you probably should write them down when you're doing your homework each time, a couple times, because writing things down also helps you memorize it. Well, I have a sum here, so I can see that a sum is part of the product rule. On the right, I have a sum, and the way I make these into a single log is I turn the arguments into factors of a log. So I have the log of 5x plus the log of 3x to the fourth. Well, this will equal the log of 5x times 3x to the fourth. That's the product rule. If I'm adding two logs, then I can turn it into a single log by turning their arguments into a product. Well, 5x times 3x to the fourth is equal to 15x to the fifth power. Okay? Product rule. So see if you can do B and C, and by hitting pause and then hitting enter again. So now in B, I have subtraction. Well, subtraction, I can see from the rules up here, is a quotient. So whatever is positive goes in the numerator, whatever's negative goes in the denominator. So for B, I have the log of 3p divided by 5q. The log, anything positive is in the numerator, 3p. Anything negative is in the denominator, 5q. And then I can make this a little bit cleaner. The last one's going to be multiple steps because I have multipliers in front, which I know are power properties, okay? So the first thing I'm going to do is bring those powers. Whenever I'm multiplying a log by times a constant, I want to pull that multiplier up as the exponent. So the first thing I'm going to do is have log of a, k to the fourth, minus log of a, m to the third. Okay, that's the power rule. I brought the multiplier that's out in front in as the exponent on the argument. Well, now I have subtraction, so I know that this is a quotient. Anything positive is in the numerator, anything negative is in the denominator, so I have the log of k to the fourth over m cubed. Okay, some of these get more involved and you're going to have to do multiple steps. This is a game I like to do to kind of practice with students, but it throws them off. Okay, the idea here is, imagine your calculator only had two buttons. It could calculate the log of 7 and the log of 5, and all of these are base 3 logs. So our goal here is to rewrite 35, or any of these arguments, in terms of 7 and 5. Well, the log of 35 is, or the number 35 is 7 times 5, okay? So I know that 35 is 7 times 5, but remember, based upon the product rule, I can make this the log of 5 plus the log of 7, because the log of a product equals the sum of the logs of each of the factors. And then I just have to add these two values. The log of 7 equals this, the log of 5 equals 1.46. Okay? In B, it's much simpler because it's already in terms of 7 and 5. So I have the log of the numerator minus the log of the denominator. And then I can plug in the values. The log of 7 is 1.77 minus 1.46. And I get 0.31. In C, I don't need to use the 7. 25 is 5 times 5, which is the log of 5 plus the log of 5, which would equal 2.92 by plugging in the 1.46 for each one. Log of 3, base 3, there's not a 7 or a 5 in there, so how can I figure this out? This is the math teacher being a little tricky. Remember, when you take the log of the base, what is the answer every time? If you don't know, go back to how we started this. Turn it into an exponential. 3 to the power of x equals 3. Well, what would be the exponent? 1. And what do we know about the log of 1? Again, we don't need 5 and 7 for this. The log of 1 is always equal to 0, because anything raised to the 0 exponent equals 1. This is just to show you the graphs of the functions. We've looked at exponential function graphs in detail in the first section of chapter 4. And because these are inverse functions, the graphs are reflective across the origin, okay? And so if you rotated the graph 90 degrees to the right and flipped it over the x-axis, you would get the inverse log, and that's the inverse graph, and that works for all functions. Okay, so this is just to show you them and how they look at each other. Okay, notice that there are no, what's important about this logarithm graph is notice that there's no negative x values. And if you put a negative number in and try to take the log of a negative number, you're not going to be able to do it, okay? You're not going to be able to do it. So let's look at one problem. The life expectancy at birth of a person born in year X is approximated by the function f of x equals 17.6 plus 12.8 times the natural log of x, where x corresponds to 1910, and this is data from the U.S. National Center for Health Statistics. Find the life expectancy of persons born in 1910, 1960, and 2010. Okay. Since you're asked for multiple values, I would suggest that you plug this formula into your calculator. This function is the life expectancy, so we're trying to find the value of f of x at specific years, x 1910, x 1960, and 2010. A big problem that students make with this, or a big mistake that students make with this problem, is they don't pay attention to the index. And they plug in 1910 for x instead of what should go in for x when it's 1910. Well, 10. So x equals 0 corresponds to 1900, because 10 is 10 years later, etc. So 1960 would be 60, and 2010 would be 110 for x. So these you can just plug into your calculator and calculate them. Since you want 3 answers, to me it's easier to plug this in once as y equals 17.6 plus 12.8 times the natural log of x, and then go to the table function on your calculator so you can just get all values from one table, and you can also check your formula to make sure you entered it correctly instead of entering it 3 times with 3 different values of x. So in 1910, the life expectancy of someone was 47 in the United States. In 1960, it had raised to 70 years old. And in 2010, it's closing in on 78, or closed in on 78, if you would. Okay, you can see those. I'm not going to spend time there. These are just plug and play. And let's look at another question from this problem. If this function remains accurate, when will life expectancy at birth be 80.2 years? Now this is again a good question or a good problem to have and to use your table. Okay, if you've plugged this function into your y equals in your calculator, you can look down your table and see when the y value hits 80.2 years. Okay, now remember that if if the entry for let's say 150 or whatever, that'd be 2050, is 80.4, and the entry for 149 is 80, then it's happening between those two periods. You're going to pick the smaller value because it's the value for x is the beginning of the year. If you say x equals 10 is 1910, when x is 10, that means that is January 1st, 1910. When x is 10.5, then it's in June. So you're going to look for the smaller value. If it's happening, if you don't actually see an 80.2 exactly in your table, then you're going to see where it happens and pick the lower x value. Another way that you can do this is enter the function into your y equals in your calculator, and then enter the constant value you want for y as another function. So y1 would equal 17.6 plus 12.8 natural log of x, and y2 would equal 80.2 years. Once you do that, if you look to the top row of your buttons and go to the far right, you have graph, and then right to the left of that you have a button that says trace, and above trace it says calc in blue. This is a function where if you hit the second button and calc, you'll see a number of functions there, and one of those calc functions is intersect, number 5. So if you do that and you graph your if you graph these, and if you can see both curves, okay, here is our logarithm curve, right? It looks like the shape of a logarithm. And the second one, y2 equals 80.2, is right here. We can see this straight horizontal line because this is the life expectancy we're looking for. And then we find the intersection. Well, if you hit the intersect button on the calc screen, it's going to give you a little flashing dot on one graph and say, is this graph 1? And then you hit enter, and then it should shift over to the other one and says, is this graph 2? And you hit enter, and then it's going to ask you if you want to guess, and then it's going to give you the answer down here. That looks like 90.2, not 80.2. I hope that's right. And we can see here it's at 133.067. Okay. Let's say this, so this is in 2033, right? X equals 10 corresponds to 1910. So x equals 133 is 123 years later, which would be 2033. Now imagine this said 133.8. You might be motivated to pick 134. You might be motivated to round this. You say, hey, it's 0.8, I should go to the next year. No, think about it. 133.8 is still happening in the year 2033. It's in the fall of that year. It's almost at the end of the year, but it's still in 2033. So you have to be careful when you're calculating these dates with these logarithms, etc.